January 5, 1943. The waters off Guadalcanal, Solomon Islands. Lieutenant Commander William Red Cochran stood at the aft 5-inch gun director aboard the USS Helena, scanning the horizon through binoculars that trembled slightly in his grip. 4 Japanese Aichi D-3, dive bombers, their distinctive fixed landing gear marking them as VALs, had just completed their attack run. One had scored a direct hit on the New Zealand cruiser Achilles. Now the VALs were departing, banking eastward at low altitude, already pulling away beyond effective range. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Standard doctrine said to conserve ammunition. The enemy was retreating. The immediate threat had passed. But Cochrane had received special orders 3 weeks earlier, orders accompanied by crates of shells marked with red bands and the cryptic designation Mark 32. He'd been told nothing about what made these shells different, only that he was to use them when the opportunity presented itself and to report the results immediately. Load Mark 32, Cochrane ordered. Target bearing 095, range 2,500 yards. Fire when ready. The gun crew moved with practiced efficiency despite their confusion. 2,500 yards was extreme range for engaging a maneuvering aircraft. The shells would need to be fused to explode at precisely the right altitude and precisely the right moment to have any chance of hitting a target that would be nearly a mile away when the rounds arrived. Except these shells hadn't been fused at all. The loader simply slammed them into the breech as is. 3 5-inch guns barked in rapid succession. Cochrane watched the shells arc across the morning sky, their trajectories taking them toward empty air behind the fleeing dive bombers. This was exactly the kind of ammunition waste that peacetime gunnery officers would have court-martialed a man for. Then the sky erupted. The first shell detonated 30 feet from the trailing VAL, a perfect airburst that sent shrapnel ripping through aluminum and flesh. The second shell exploded even closer. The third was almost redundant. The VAL disintegrated in mid-air, pieces tumbling into the Pacific like confetti. The other 3 dive bombers fled at maximum speed, while Cochrane and his gun crew stared in stunned silence at what they'd just witnessed. They had fired 3 shells at a distant, retreating target with no manual range setting, no fuse calculation, no firing table consultation, and they'd scored a kill that should have been statistically impossible. What Cochrane didn't know, what couldn't be explained to him for another year due to security restrictions second only to the Manhattan Project itself, was that those 3 shells contained tiny radio transmitters, powered by vacuum tubes designed to survive 20,000 G-forces. Each shell had detonated itself automatically when it passed within lethal range of the target. The United States had just introduced the proximity fuse to combat, and warfare would never be the same. But the story of how America developed a weapon that let gunners hit targets by seemingly shooting at nothing begins not in the Pacific in 1943, but in the skies over Britain 3 years earlier, when it became horrifyingly clear that existing anti-aircraft defenses were failing catastrophically. The mathematics of shooting down aircraft in 1940 had remained essentially unchanged since the First World War. An anti-aircraft gun fired a shell with a mechanical time fuse, essentially a tiny clockwork mechanism that would detonate the shell after a predetermined number of seconds. The gun crew had to calculate the exact time the shell would take to reach the target's altitude, set that time on the fuse manually using a special wrench, load the shell, and fire, before the target's position changed enough to make the calculation obsolete. This process required the gunner to predict where a maneuvering aircraft would be several seconds in the future, calculate the ballistic trajectory of the shell, accounting for wind, air density, and the Earth's rotation, then manually set a mechanical timer accurate to a fraction of a second. If any variable in this chain of calculations was wrong by even a small margin, the shell would explode harmlessly hundreds of feet from its target. The British learned exactly how inadequate this system was during the Battle of Britain. German bombers attacked London throughout the summer and fall of 1940, and British anti-aircraft batteries fired back with everything they had. Official British assessments at the start of the Blitz estimated that it took approximately 20,000 anti-aircraft rounds to shoot down a single German aircraft. 20,000 rounds. Some estimates ranged as high as 100,000 rounds per kill, while the most optimistic British analysts suggested the figure might be as low as 2,500. The best gunners in the world, firing from fixed defensive positions with pre-calculated firing tables and advanced range-finding equipment, needed thousands of shells to destroy one bomber. The implications were staggering from both a logistical and tactical perspective. Britain's factories simply could not produce anti-aircraft ammunition fast enough to sustain those expenditure rates indefinitely. More critically, German bombers could operate with near impunity, knowing that the statistical probability of being hit by anti-aircraft fire was negligible. Contact fuses were equally useless. A contact fuse detonated only when the shell physically struck something, which meant achieving a direct hit on an aircraft moving at 200 miles per hour at altitudes between 10 and 30,000 feet. The projectile itself was perhaps 6 inches in diameter, the aircraft a target perhaps 60 feet long. A miss by even a few feet meant the shell would pass harmlessly by and fall to earth without detonating. Gunnery officers joked grimly that it would be easier to hit a specific brick on a specific building than to achieve a contact hit on a maneuvering bomber. The British recognized the problem and began working on a solution in 1939. What they needed was a fuse that could detonate automatically when it came close to a target, eliminating the need for precise manual time setting and turning near misses into kills. The concept was called a proximity fuse, and it required solving engineering problems that seemed impossible with 1939 technology. The technical challenges were formidable. The fuse would need to contain a detection system sophisticated enough to sense an aircraft's presence at lethal range. It would need an electronic circuit to trigger detonation at exactly the right moment. It would need a power source compact enough to fit in a 5-inch artillery shell, but reliable enough to work after months in storage. And all of these components would need to survive being fired from a gun. That last requirement was the deal-breaker. When an artillery shell is fired, the acceleration forces inside the gun barrel reach 20,000 g-forces, meaning every component experiences 20,000 times its own weight pressing on it for a fraction of a second. Then the shell begins rotating at 25,000 revolutions per minute as it travels through the rifled barrel. Electronic components in 1939 simply could not survive these forces. Vacuum tubes shattered, batteries ruptured, circuits tore themselves apart. The British experimented with several approaches. Photoelectric fuses that would detect changes in light as they approached a target showed promise for daytime use, but they were useless at night or in cloud cover. Acoustic fuses that listened for engine noise proved too unreliable. Electrostatic fuses that measured changes in the electric field near an aircraft worked in laboratory conditions, but failed when tested in actual shells. By 1940, British scientists had concluded that developing a practical proximity fuse might take years, and Britain did not have years. The Luftwaffe was bombing London every night. The Americans entered the proximity fuse race in February 1940 when Dr. Merle Tuve, director of the Department of Terrestrial Magnetism at the Carnegie Institution in Washington, received an urgent request from the National Defense Research Committee. The committee had been briefed on British proximity fuse research and recognized that America needed a crash program to develop its own version. Tuve assembled a team of physicists and engineers and set up a laboratory that would eventually be designated Section T, operating under security restrictions that prohibited even mentioning the project's existence. Section T approached the problem from a different angle. Instead of trying to make existing technology survive the forces of gun firing, they would design new technology specifically to withstand those forces. The fuse would use radio waves, not light or sound. A tiny transmitter in the nose of the shell would broadcast a continuous radio signal. When the shell approached a target, the radio waves would reflect back, and the fuse would detect the change in signal strength. This was the same principle behind radar, miniaturized to fit in a 5-inch artillery shell. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The engineering challenges seemed insurmountable. Radio transmitters in 1940 were typically the size of a filing cabinet. Section T needed to fit a complete radio system into a space smaller than a coffee cup. The transmitter would need to generate enough power to detect aircraft at useful ranges, but it could only draw power from a battery about the size of 4 stacked quarters. The receiver would need to be sensitive enough to detect reflected signals, but not so sensitive that it would be overwhelmed by the shell's own transmission or triggered by false reflections from waves or ground clutter. Then there was the vacuum tube problem. Vacuum tubes, the electronic switches that made radios and early computers possible, were notoriously fragile. They consisted of thin glass envelopes containing delicate metal filaments and grids suspended in a vacuum. Drop a vacuum tube on a table, and it would likely break. Subject it to 20,000 G-forces, and it would atomize. Yet Section T needed vacuum tubes that could not only survive being fired from a gun, but continue functioning afterward. Dr. Lawrence Hafstad, one of Fuze's key engineers, led the vacuum tube development effort. His team started with commercial radio tubes and methodically reinforced every component. They shortened the filaments so they would be less likely to snap under acceleration. They moved the tubes, elements closer together so they would have less distance to travel if they did break loose. They experimented with different glass compositions, seeking a formula that could flex slightly under stress without shattering. They tested hundreds of variations, firing them from guns mounted in test ranges, measuring which ones survived and which ones disintegrated. By late 1940, Hafstad's team had created what they called a ruggedized vacuum tube, a stubby component barely an inch long that looked nothing like commercial radio tubes. Early tests were encouraging. The tubes survived being fired, though their failure rate was still unacceptably high. About 30% would shatter or stop functioning. Still, it was progress. Commercial tubes had a failure rate of 100% when fired from guns. The transmitter design posed different challenges. Section T settled on a frequency around 180 to 220 MHz, high enough that the antenna could be very small, low enough that the required electronic components could be miniaturized with 1940 technology. The shell's body would serve as the antenna, an elegant solution that saved space and weight. But making this work required precise machining and careful positioning of every component. Dr. Fuze's team decided that the Fuze would detect changes in the Doppler effect. When a radio transmitter moves toward a reflecting object, the reflected waves interfere with the transmitted waves in a predictable pattern. Every half wavelength in distance, roughly 0.7 meters at the chosen frequency, the signal would peak and fade. This cycling happened at a frequency between 200 and 800 Hz, creating an audio frequency signal that could trigger the detonation circuit. The circuit design was brutally simple by necessity. Too many components meant more weight, more power consumption, and more things that could break under the acceleration, firing. Section T engineers created a circuit with just enough components to amplify the Doppler signal, filter out noise, and trigger the detonator when the signal exceeded a predetermined threshold. The entire circuit, including vacuum tubes, resistors, capacitors, and detonator, would need to fit in a package about 4 inches long and 2 inches in diameter. Power came from a specially designed battery. Standard batteries of the era used wet cell technology, liquid electrolyte between metal plates. Firing a shell would slam the liquid to one end of the battery with 20,000 G-forces, shorting the cells and destroying the battery instantly. Section T engineers developed dry cell batteries with gel electrolyte that could withstand the forces, though these had a shorter shelf life than wet cells. Later versions would use reserve batteries, where the electrolyte was stored separately and only mixed with the battery plates when an impact-activated mechanism broke a barrier between them, solving the shelf life problem. Safety was paramount. The Fuze had to be completely inert during handling and transport. It could not detonate accidentally if dropped, if exposed to electrical interference, or if struck by shrapnel. It had to remain safe, even if the ship carrying it took a direct hit, but once fired, it had to arm itself within a few seconds and be ready to detonate at exactly the right moment. Section T designed multiple safety mechanisms. The Fuze would only arm after experiencing the acceleration of being fired from a gun. No acceleration, no arming. The centrifugal force from the shell's rotation would spin a mechanical safety out of the way, physically closing a circuit that couldn't be completed any other way. The power supply wouldn't activate until both acceleration and rotation had occurred. These interlocking safeties meant that the fuse couldn't possibly detonate until it had been fired from a gun and was spinning through the air. The first, complete prototype, designated the Mark 32, was ready for testing in August 1941. The fuse measured 5.5 inches long and 2 inches in diameter, weighted about 3 pounds, and fit inside the nose cone of a standard 5-inch anti-aircraft shell. It contained 5 vacuum tubes, a small transmitter circuit, a receiver circuit, an amplifier, a battery, and the detonator. The entire assembly cost about $732 to manufacture, an astronomical sum in 1941, equivalent to roughly $13,000 today. The first tests were disasters. Fuses failed to arm, vacuum tubes shattered, batteries leaked, circuits shorted. The few that did function properly either detonated prematurely or failed to detonate at all. Section T went back to the drawing board, redesigning components, strengthening weak points, and refining the circuit. Each iteration required months of design work, followed by weeks of testing. 1. Persistent problem was premature detonation when firing at low angles over water. The fuse would detect reflections from ocean waves and detonate before reaching the target. Section T engineer Ralph Baldwin developed what was called the wave suppression circuit, essentially an automatic volume control that would reduce the fuse's sensitivity to weak signals from waves while maintaining sensitivity to the strong reflections from aircraft. This circuit, added in late 1943, largely solved the wave reflection problem. By mid-1942, after hundreds of design iterations and thousands of test firings, the Mark 32 fuse was functioning reliably enough for production. The failure rate was down to about 30%, which was considered acceptable for a first-generation revolutionary weapon. Crosley Corporation, a radio manufacturer in Cincinnati, received the first production contract. By September 1942, the first combat-ready VT fuses, as they were now codenamed, were rolling off the production line. VT stood for variable time, a deliberate piece of misdirection. If the Germans captured a dud shell and examined the fuse, they would assume it was some kind of improved mechanical timer, not a miniature radio transmitter. The red bands painted on VT-fused shells warned ammunition handlers that these were special weapons, requiring careful handling, but gave no indication of what made them special. The first shipment of 5,000 VT fuses arrived at Pearl Harbor in November 1942. Admiral William Bull Halsey, commanding the South Pacific Force, was briefed on their capabilities and given strict instructions about their use. VT fuses could only be fired over water where dud shells would sink before the enemy could recover them. Under no circumstances were they to be used over land, where an intact fuse might fall into enemy hands. The technology was too valuable to risk compromise. Halsey distributed the fuses to his cruiser and destroyer commanders, with orders to test them in combat and report results. The USS Helena, a Brooklyn-class light cruiser mounting 12 5-inch guns, received several hundred VT-fused shells in late December 1942. Her gunnery officer, Lieutenant Commander William Cochran, was given minimal briefing. Load them, fire them, report what happens. He wasn't told how they worked or what made them different from conventional shells. He was simply ordered to use them when Japanese aircraft attacked and see if they performed better than standard anti-aircraft ammunition. January 5, 1943 provided the answer. 3 shells, 3 hits, 1 confirmed kill, all at ranges where conventional anti-aircraft fire would have been ineffective. Cochran's after-action report described the engagement in almost disbelieving terms. The shells appeared to detonate automatically near the target, producing far superior results compared to standard ammunition. This brief combat report made its way up the chain of command to Washington, where Dr. Fuze and his Section T team received confirmation that 2 years of exhausting engineering work had produced a weapon that actually functioned in combat. The Helena kill was important not just because it proved the technology worked, but because it demonstrated the tactical advantage that proximity fuses provided. Conventional anti-aircraft gunnery required the target to be within range long enough for fire control crews to calculate a firing solution, set fuses, and fire multiple salvos with corrections based on observed burst patterns. A retreating aircraft could often escape before this time-consuming process could be completed. VT fuses eliminated most of that delay. Point the gun at the target, fire, and let the shells handle their own detonation. Engagement times dropped from minutes to seconds. Over the following months, more American cruisers and destroyers received VT-fused ammunition. Combat reports consistently showed dramatic improvements in kill rates. During 1943, the Navy fired 9,128 rounds of VT-fused ammunition, downing 61 Japanese aircraft, 155 rounds per kill. Compare this to conventional time-fused ammunition, which required 508 rounds per kill during the same period. The VT fuse was more than 3 times as effective as conventional ammunition, and this figure would improve as crews gained experience with the new weapon. Admiral Arleigh Burke, who would later become Chief of Naval Operations, served as Chief of Staff to Admiral Mark Mitcher, commanding the fast carrier task forces during the latter part of the war. In a 1978 interview, Burke described the impact of VT fuses on carrier task force operations. All the 5-inch, 38 and 5-inch, 25 ammunition was fitted with VT fuses, and as you well know, those fuses knocked down enemy planes by the dozens. The VT fuse changed everything about carrier defense. Before the fuse, we were desperately concerned about nighttime torpedo plane attacks. Japanese pilots would come in low over the water where our fire control radars struggled to track them. With VT fuses and improved radar, suddenly we could destroy nighttime attackers reliably. Admiral Halsey had been deeply concerned about torpedo plane threats, and the VT fuse gave us confidence we could defend the fleet. The Pacific Theater provided ideal conditions for VT fuse deployment. Naval battles occurred over open ocean where dud shells would sink rather than fall into enemy hands. Japanese aircraft frequently attacked at dawn or dusk, when visibility made conventional anti-aircraft fire less effective. Kamikaze tactics, which began in late 1944, required ships to defend themselves against fast-moving, determined attackers that would not evade or break off. VT fuses proved devastatingly effective against these suicide attackers. The engagement off Okinawa on May 11, 1945, demonstrated exactly how powerful VT fuses had become. 2 American destroyers, the USS Hadley and USS Evans, found themselves defending 4 small support vessels against a massive kamikaze attack. Fighter direction radar counted 156 Japanese aircraft incoming. The 2 destroyers and their crews prepared for what appeared to be certain annihilation. Instead, they fought for 90 minutes and survived. The after-action report documented the fury of the engagement. The Evans knocked down 23 enemy aircraft before taking 4 kamikaze hits that disabled her and forced her withdrawal. The Hadley destroyed 12 attackers. Between the 2 destroyers, they fired thousands of rounds of VT-fused 5-inch ammunition, along with countless short-range shells from automatic weapons. Every 5-inch round that came close to a target automatically detonated with shrapnel-spreading effect. Japanese pilots found themselves flying through a sky filled with explosive airbursts timed and positioned with inhuman precision. The battle nearly destroyed both ships. The Evans lost 30 men killed and many more wounded. The Hadley's casualties were similarly severe, but they had survived an attack by odds that should have overwhelmed them completely. The fleet commander's verdict on the role of VT-fused ammunition in the engagement was direct and unambiguous: indispensable. Statistics from the Pacific Campaign revealed the full effectiveness of the proximity fuse. Between October 1944 and August 1945, VT-fused projectiles destroyed 278 Japanese aircraft. Analysis estimated that only 46 of these would have been destroyed if time-fused projectiles had been employed. The VT fuse was 6 times more effective than conventional ammunition, assuming a 70, fuse reliability rate. Even if the failure rate was higher, closer to 50%, which was the Navy's minimum acceptable threshold, the effectiveness ratio was still approximately 4-1. The numbers told a story of tactical revolution. During 1944, as VT Fuze production ramped up, the Navy fired 32,826 VT fused rounds. Kill rates averaged 421 rounds per aircraft destroyed, higher than 1943's figure, primarily because doctrine had shifted toward opening fire earlier, enabled by American logistical superiority that made ammunition expenditure less of a concern. The goal wasn't ammunition economy. It was ensuring that no Japanese aircraft reached American ships. The final year of the war saw VT fuse usage accelerate dramatically. Nearly 2/3 of all VT fuses expended during the war were fired in just 7.5 months, destroying over 200 aircraft and revealing another tactical advantage that fire control designers hadn't anticipated. Previously, large-caliber anti-aircraft guns required sophisticated four-dimensional tracking systems. These systems were large, expensive, and slow to acquire targets. Short-range threats required faster responses, which was why ships carried numerous automatic weapons like 20mm and 40mm guns with simple directors. VT fuses bridged the gap between heavy and light anti-aircraft weapons. Because VT-fused shells didn't need to be set before firing, simple angle-only directors like the Mark 51 could control 5-inch guns. The last year of the war saw many ships connecting light directors to their main battery guns, multiplying the number of targets they could engage simultaneously and slashing response time from minutes to seconds. A ship that had previously been able to engage perhaps 2 targets simultaneously could now engage 6 or 8. The fleet's defensive firepower had effectively tripled without adding a single gun. But while the Navy was achieving spectacular results in the Pacific, the technology remained forbidden for use over land. The Army Air Forces had demanded that proximity fuses never be used where unexploded shells might fall into enemy hands. This restriction frustrated ground force commanders who recognized that VT fuses could revolutionize not just anti-aircraft defense, but also conventional artillery bombardment. A shell that automatically detonated 30 to 50 feet above the ground would shower shrapnel over a wide area, far more effective against infantry and light vehicles than impact-fused shells that had to detonate on contact with the ground. The restriction held through most of 1944 despite repeated requests from field commanders. Then Germany gave the Allies a reason to reconsider. On June 13, 1944, 1 week after D-Day, a small aircraft appeared over London, flying at approximately 400 miles per hour with a distinctive buzzing sound. It was a Vergeltungswaffeins, the Vone, Hitler's vengeance weapon. An unmanned cruise missile loaded with 1 ton of high explosives, the Vone was designed to terrorize British civilians and undermine morale. Traditional anti-aircraft defenses struggled against V-1s. The missiles flew too fast for most fighters to catch unless they had altitude advantage. They flew too low and too fast for conventional anti-aircraft gunnery to track effectively. Time-fused shells required precise calculation of the missile's position and speed, difficult when the target was barely giving radar operators time to spot it before it crossed the coast. The British needed something better, and they needed it immediately. Why you? Pilots started wasting ammo on empty sky and shot down 800-plus planes in 6 months, Part 2 final. On June 12, 1944, just 6 days after the first Vone struck London, the United States authorized the use of proximity fuses over land for the specific purpose of defending Britain against the flying bombs. The restriction was carefully calculated. British anti-aircraft guns were deployed in a long coastal belt along the southeastern approaches to London, with the Channel and North Sea behind them. Dud shells would fall into water rather than land where Germans could recover them. Fighter aircraft patrolled inland, leaving the coastal zone as a pure anti-aircraft engagement area. The deployment was rushed. Section T engineers had to modify fuses to fit British 3.7-inch guns and American 90mm guns. Production facilities at Crosley Corporation in Cincinnati worked around the clock to manufacture the modified fuses. British Prime Minister Winston Churchill personally authorised special Lancaster bomber flights to transport the Fuzes from America to Britain, bypassing slower sea transport. The first week of VT Fuze defence against V-1s produced modest results. Anti-aircraft batteries destroyed 24% of incoming missiles, better than before but hardly decisive. But the gunners were learning. VT fuses didn't require the precise timing and prediction that conventional fuses demanded. Crews could fire more quickly, engage targets at longer ranges, and trust the shells to detonate themselves at the optimal position. By the second week, kill rates climbed to 40%. By the third week, 55%. By the end of the fourth week, British anti-aircraft batteries were destroying 79% of V-1s that entered their engagement zone. On the last day that large numbers of V-1s were launched against England, radar detected 104 missiles approaching the coast. 68 were destroyed by VT-fused anti-aircraft fire. Of the remainder, only 4 reached London. The Vone campaign against London launched 9,300 missiles between June and late August 1944. The combination of VT fuses, improved radar, and radar-controlled gun directors transformed what could have been a catastrophic bombardment into a manageable threat. Churchill would later write, "These so-called proximity fuses, made in the United States, proved potent against the small unmanned aircraft with which we were assailed in 1944. The technology had saved London. As German forces retreated from France, they redirected Vone attacks toward Antwerp, the Belgian port critical for supplying Allied armies advancing toward Germany. In September 1944, the British 11th Armoured Division defending Antwerp came under intense Vone bombardment. They needed VT fuses immediately, but modified for their specific anti-aircraft guns. Crosley Corporation received an emergency order and had modified fuses in production within days. Lancaster bombers again provided express transport from Cincinnati to Europe. A single anti-aircraft unit defending. Antwerp destroyed 48 of the first 75 V-1s they encountered using VT-fused ammunition. The port remained operational throughout the campaign, enabling Allied logistics to sustain the final push into Germany. Between June 1944 and March 1945, anti-aircraft batteries using VT fuses destroyed over 2,000 V-1s. Without this capability, the missile attacks might have disrupted Allied operations severely, possibly delaying the end of the war by months. But the true test of VT fuse effectiveness on the European continent came in December 1944, when Germany launched its final major offensive through the Ardennes forest. The Battle of the Bulge began on December 16th with a massive German armoured thrust aimed at splitting the Allied armies and capturing the port of Antwerp. German commanders hoped that bad weather would ground Allied air power, negating one of the Allies' decisive advantages. For the offensive's first several days, fog and snow did exactly that, allowing German forces to advance under cover of weather. Hitler ordered the Luftwaffe to support the offensive with whatever forces it could muster. Hundreds of German fighters and bombers, many flown by inexperienced pilots pulled from training units, launched attacks against Allied positions. This was exactly the scenario that American commanders had been warning about: German aircraft attacking Allied ground forces in areas where dud shells might fall into enemy hands. The Pentagon had repeatedly refused requests to authorize VT fuse use over land for precisely this reason. Colonel George Axelson commanded the 406th Artillery Group near Monschau, Germany. On the morning of December 16th, as German forces smashed into the 38th Cavalry Squadron's positions, Axelson faced a decision. His unit had recently received VT-fused anti-aircraft ammunition, with strict orders not to use it until official authorization came from higher command. But the cavalry troopers were being overrun. They needed anti-aircraft support immediately. The authorization might not come in time. Axelson ordered his gunners to load VT-fused shells and engage any German aircraft that appeared. Within hours, 406th Artillery Group was downing German planes with startling efficiency. Word spread quickly through American artillery units that VT fuses worked as advertised and that at least one commander was using them despite the restrictions. Other units began using their VT stocks as well, gambling that the emergency justified breaking protocol. General Dwight Eisenhower, Supreme Allied Commander in Europe, learned about the unauthorized VT fuse use on December 18th. Rather than reprimand the commanders who'd broken security restrictions, Eisenhower immediately contacted Washington, demanding official authorization to use VT fuses without restriction. His message was blunt. German forces were launching their largest offensive since D-Day. The Luftwaffe was flying in support. Allied troops needed every advantage available. The risk of compromising the technology was acceptable given the stakes. The Pentagon lifted all restrictions on VT fuse use on December 21, 1944. From that moment until the end of the war in Europe, American forces used proximity fuses freely for both anti-aircraft defense and ground bombardment. The effect on German forces was immediate and devastating. General George Patton, commanding the Third Army, wrote to the War Department describing the new weapon's effectiveness. "The new shell with the funny fuse is devastating. We caught a German battalion which was trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." Patton was describing VT-fused artillery shells used for ground bombardment rather than anti-aircraft defense, but the principle was identical. Shells that automatically detonated 30 to 50 feet above the ground created airbursts that showered shrapnel over wide areas. German soldiers who had felt relatively safe in foxholes and trenches from conventional artillery found themselves exposed to a weapon against which there was no effective defense. One German prisoner described VT-fused bombardment as quick, powerful bursts for which there was simply no defense. Another report from captured German documents noted that soldiers began refusing orders to leave bunkers during artillery bombardments, recognizing that the new American shells made movement during bombardment suicidal. The psychological impact was as significant as the physical damage, but it was in anti-aircraft defense that VT fuses achieved their most spectacular results on the European continent. From December 21, 1944, when restrictions were lifted, until Allied forces crossed the Rhine in March 1945, proximity-fused anti-aircraft fire destroyed more than 1,000 German aircraft. This figure exceeded the total number of Luftwaffe aircraft destroyed by VT fuses in the entire Pacific campaign, despite the European theatre's use lasting less than 4 months. The math was remarkable. During the Battle of the Bulge specifically, Allied anti-aircraft artillery destroyed 417 German aircraft. This represented the majority of Luftwaffe losses during the offensive and effectively neutralized German air support for their ground forces. Many of these kills came from American artillery batteries that had previously struggled to hit high-altitude bombers with conventional time-fused ammunition. VT fuses made every artillery battery a dangerous anti-aircraft threat. The Luftwaffe's final major operation, the New Year's Day attack of 1945, known as Operation Bodenplatte, demonstrated the changing calculus of air warfare. Germany launched over 450 fighters in a dawn raid against Allied airfields in France, Belgium, and Holland. The attack destroyed over 400 Allied aircraft on the ground, a tactical success. But the Luftwaffe lost 237 aircraft in the operation, including 59 experienced commanders. The kill ratio was unsustainable. Many of those Luftwaffe losses came from anti-aircraft fire as German aircraft withdrew from their attacks. VT-fused shells caught formation after formation of German fighters as they retreated at low altitude, exactly the scenario where conventional anti-aircraft fire had been least effective. German pilots reported encountering walls of exploding shells that seemed to track their aircraft with impossible accuracy. They were experiencing what Lieutenant Commander Cochrane had unleashed on that Japanese dive bomber 2 years earlier, except now on a massive scale. The statistical comparison between conventional and VT-fused ammunition in Europe was even more dramatic than in the Pacific. Army studies conducted after the war analyzed anti-aircraft effectiveness during the Battle of the Bulge and subsequent operations. VT-fused ammunition averaged approximately 300 rounds fired per aircraft destroyed. Conventional time-fused ammunition had historically required between 2,000 and 25,000 rounds per kill, depending on conditions and crew training. Even using the most conservative figures, VT fuses were at least 6 times more effective than conventional ammunition. Production numbers illustrated how thoroughly VT fuses had been integrated into American military doctrine by 1945. Over 22 million proximity fuses were manufactured during the war by more than 100 companies. Crosley Corporation, the original contractor, produced the most, but they were joined by RCA, Eastman, Kodak, McQueen-Norris, Sylvania, and dozens of smaller firms. The cost per fuse had dropped from $732 for the first prototypes to approximately $18 by 1945, making them economically viable for mass production. The fuse had become one of the first mass production applications of printed circuits, a manufacturing technique that would revolutionize electronics in the post-war era. Assembly lines in Ipswich, Massachusetts, produced over 5 million fuses, the most of any single location. Women workers, many of whom had never handled electronics before, learned to solder the tiny circuits and assemble the vacuum tubes under magnification. The work was classified so highly that many workers didn't know what they were building, only that it was vital to the war effort. Procurement contracts for VT fuses grew from $60 million in 1942 to $200 million in 1943, $300 million in 1944, and $450 million in 1945. The total cost approached $1 billion, equivalent to approximately $14 billion in 2025. Only the Manhattan Project and radar development consumed more resources during the war. Yet unlike those programs, VT fuses provided immediate, quantifiable tactical advantages that could be measured in aircraft destroyed and lives saved. The impact extended beyond simple kill statistics. VT fuses changed how naval task forces operated. Before their introduction, carrier task forces had to maintain heavy combat air patrols to defend against air attack, pulling fighters away from offensive missions. Admirals worried constantly about nighttime torpedo plane attacks when fighters couldn't provide effective defense. VT-fused anti-aircraft fire provided a defensive baseline that allowed carriers to reduce defensive patrols and commit more aircraft to offensive operations. Ground forces benefited similarly. Artillery batteries that had previously been dedicated to direct fire support could engage aircraft effectively, reducing the need for specialized anti-aircraft units. This freed manpower and equipment for other roles while improving overall defensive capability. The psychological effect on enemy pilots was significant. German and Japanese aviators both reported that American anti-aircraft fire had become dramatically more dangerous starting in late 1944, forcing them to operate at higher altitudes or abandon certain attack profiles entirely. The technology's influence on post-war weapons development was profound. Every major military power recognized that proximity fuses had changed warfare permanently. The Soviet Union, which had captured several VT-fused shells during the war, began their own proximity fuse development program immediately after hostilities ended. Britain, which had access to American VT fuse technology through wartime cooperation, continued developing their own variants. France, Germany, and eventually every nation with an advanced military would field proximity-fused ammunition. Modern military aviation owes much to lessons learned from VT fuse effectiveness. The concept of automated target detection and detonation led directly to guided missile development. The AIM-54 Phoenix air-to-air missile, the standard surface-to-air missile systems, and the Patriot missile all use sophisticated proximity fuse technology, descended from those first Mark 32 fuses fired by the USS Helena. The Gulf War's success with Patriot missiles intercepting Iraqi Scuds demonstrated proximity fuse principles applied to missile defense. The engineering breakthroughs required to create VT fuses accelerated electronics miniaturization. Designing circuits and vacuum tubes that could withstand 20,000 G-forces required innovations in materials, science, circuit design, and manufacturing techniques that influenced civilian electronics development for decades. The same companies that built VT fuses, Crosley, RCA, Sylvania, would dominate post-war consumer electronics markets, applying lessons learned from military production to radios, televisions, and eventually solid-state devices. Perhaps most significantly, VT fuses demonstrated that revolutionary weapons technology could be developed, produced in massive quantities, and deployed effectively in under 4 years. From Dr. Fuze's first experiments in 1940 to the massive production runs of 1944 represented an engineering and manufacturing achievement that would serve as a model for Cold War weapons development. The Manhattan Project followed a similar timeline and organizational structure. Radar development paralleled the proximity fuse program in many ways. The Pentagon had learned that focused research programs with adequate funding and clear objectives could produce war-winning technologies on compressed timelines. Secretary of the Navy James Forrestal summarized the proximity fuse's contribution in simple terms. The proximity fuse has helped blaze the trail to Japan. Without the protection this ingenious device has given the surface ships of the fleet, our westward push could not have been so swift, and the cost in men and ships would have been immeasurably greater. This was not hyperbole. Without VT fuses, the Navy's island-hopping campaign across the Pacific would have faced far higher casualties from Japanese air attacks. The kamikazes that devastated so many ships despite VT fuse defenses would have been even more destructive with only conventional anti-aircraft ammunition available. General Eisenhower's assessment was equally direct, though more speculative. It seemed likely that if the German had succeeded in perfecting and using these new weapons 6 months earlier than he did, our invasion of Europe would have proven exceedingly difficult, perhaps impossible. Was referring to the Vone and V2 missiles, but the statement applied equally to proximity fuses. If Germany had developed VT fuses first and deployed them against Allied bomber formations in 1943, the strategic bombing campaign might have been impossible. The casualty rates that Allied bombers suffered even without proximity-fused German defences were barely sustainable. Adding VT fuses to German anti-aircraft batteries might have made daylight bombing suicidal. The story of the proximity fuse is ultimately about the compound effect of small improvements. Each individual component, the ruggedized vacuum tube, the miniaturized transmitter, the automatic volume control circuit, the reserve battery, represented incremental progress. None were revolutionary individually. Together, they created a weapon system that increased anti-aircraft effectiveness by factors ranging from 3 to 10 depending on conditions. This multiplier effect changed the tactical and strategic calculus of air warfare. Consider Lieutenant Commander Cochrane's engagement on January 5, 1943. Under conventional doctrine, he would not have fired at those retreating dive bombers. They were beyond effective range, moving away, no longer threatening the Helena. Expending ammunition on such a target would have been wasteful. But VT fuses changed the equation. Now those same targets were killable with reasonable ammunition expenditure. The effective engagement envelope had expanded dramatically in both range and timing. This expansion of the engagement envelope had cascading effects throughout military operations. Aircraft that had previously been safe once they broke contact with their targets were now vulnerable throughout their entire flight profile. Pilots could no longer rely on distance or darkness for protection. The sky itself had become more dangerous for anyone flying within range of ships or ground units equipped with VT-fused ammunition. This forced changes in aircraft design, mission planning, and tactics that would persist long after World War II ended. The irony of the proximity fuse's nickname, the funny fuse, reflects how revolutionary technology often appears mundane to the soldiers using it. To gunners loading shells, VT fuses looked almost identical to conventional ammunition, same size, same weight, same loading procedure. The red bands painted on them indicated they were special, but nothing about their external appearance suggested they contained miniature radio transmitters and shock-resistant electronics. They were just shells that worked better than regular shells. The funny part was how well they worked. General Patton's assessment that VT fuses would require some new method of warfare proved prescient. Proximity-fused weapons did change warfare, though not in ways that were immediately obvious. The real revolution was in shifting tactical calculations. When near misses become kills, when engagement ranges expand, when ammunition effectiveness multiplies by factors of 3 to 10, every assumption about force ratios, defensive positioning, and acceptable risk changes. Military planners had to rethink air defense, artillery employment, and force structure to account for the new capabilities. The German and Japanese responses to VT fuses revealed how difficult it was to counter the technology. Both nations attempted to develop proximity fuses of their own, but neither succeeded in fielding them in significant numbers before the war ended. Germany made more progress, developing electrostatic proximity fuses for their anti-aircraft rockets, but production never reached useful scale. Japan's industrial base was too degraded by 1944 to undertake the precision manufacturing required. Neither nation developed effective countermeasures against VT fuses. The Germans captured several dud VT-fused shells during the Battle of the Bulge and immediately began studying them. German engineers correctly identified the operating principle and recognized the technology was American rather than British, based on manufacturing techniques and component design. But knowing how the fuse worked didn't provide a way to defend against it. You can't jam a proximity fuse. You can't decoy it. You can only avoid entering its engagement range, which meant avoiding anti-aircraft fire entirely. This inability to counter VT fuses forced both Germany and Japan to modify their air tactics in ways that reduced their effectiveness. Aircraft had to fly higher to stay above the effective range of ground-based anti-aircraft fire, reducing bombing accuracy. Strike aircraft had to employ high-speed approaches and rapid egress to minimize time in the engagement zone, reducing their ability to attack defended targets effectively. Fighter aircraft found themselves vulnerable to anti-aircraft fire during strafing runs, making ground attack missions more dangerous. Each tactical adjustment imposed costs in reduced effectiveness or increased casualties. The proximity fuse represented one of those rare technological developments that fundamentally advantaged one side in a conflict without the opponent being able to respond effectively. Germany and Japan never fielded an equivalent capability. They never developed countermeasures. They could only accept that American anti-aircraft defenses had become dramatically more lethal and adjust their operations accordingly. This asymmetric advantage, combined with Allied advantages in radar, logistics, and industrial production, made the final year of the war increasingly one-sided, despite fierce tactical resistance. Looking back from 80 years later, the proximity fuse's legacy remains embedded in military technology and doctrine. Every modern air defense system uses some form of automated target detection and detonation. The principle of using electronics to improve weapons accuracy has been applied to everything from cruise, missiles to artillery shells to aerial bombs. The engineering lessons learned from miniaturizing electronics to survive extreme acceleration influenced everything from space exploration to consumer devices. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.